This is an audio recording for visually impaired students. Physical Chemistry, Chapter 3, Molecular Spectroscopy. General Introduction. Spectroscopy is that branch of science which deals with the study of interaction of electromagnetic radiation with matter. Heading 3.1, Electromagnetic Radiation. The term electromagnetic radiation represents the radiant energy emitted from any source in the form of light, heat, etc. Some important characteristics of these electromagnetic radiations are given below. First, they have dual character, that is, particle character as well as wave character. For example, a beam of light is a stream of particles called photons moving through the space in the form of waves. Second, these waves are associated with electric and magnetic fields oscillating perpendicular to each other and also perpendicular to the direction of propagation as shown in figure 3.1. That is why they are called electromagnetic waves. Third, all electromagnetic radiation travel with the velocity of light, that is c. Fourth, the wavelength lambda of the electromagnetic radiation is related to their frequency nu and velocity c. According to this equation, c is equals to nu lambda, or lambda is equals to c upon nu, or nu is equals to c upon lambda. As the quantity 1 upon lambda is equals to nu bar is called wave number, hence nu is equals to c nu bar. It is still very common to express nu bar in terms of non-SI unit, centimeter per centimeter. When lambda is in centimeter and c is in centimeter per second, frequency nu has the units per second. Fifth, as stated earlier, electromagnetic radiation are made up of photons. Each photon is a packet of energy whose energy is given by Planck's equation E is equals to h nu, where h is Planck's constant, which is 6.6262 into 10 raised to power minus 34 joule second. Heading 3.2, Reasons of electromagnetic spectrum. When the different types of electromagnetic radiations are arranged in order of their increasing wavelengths or decreasing frequencies, the complete arrangement is called electromagnetic spectrum. The reasons into which the electromagnetic radiation have been classified is on the basis of their source and detectors required. These limits are given in table 3.1. The different radiations differ in their physical and chemical effects because they possess different energies. The energy of a photon being E is equals to h nu, which is equals to hc nu bar, where nu bar represents the wave number. Table 3.1, Reasons of electromagnetic spectrum. Electromagnetic radiation, cosmic rays, have wavelength 0 to 0.001 and the frequency infinity to 3 into 10 raised to power 21. The source present in the outer space. Gamma rays, wavelength 0.0001 to 0.1 with frequency 3 into 10 raised to power 22 to 3 into 10 raised to power 19. Source is radioactive substances. Next is X-rays with wavelength 0.001 to 100 with frequency 3 into 10 raised to power 20 to 3 into 10 raised to power 12, and the source is bombardment of certain metals with cathode rays. Next is ultraviolet rays with wavelength 1 to 3800 and frequency 3 into 10 raised to power 12 to 7.9 into 10 raised to power 14, and the source is hydrogen or deuterium discharge tube or a component of sun's rays. Visible light have wavelength 3800 to 7600 with frequency 7.9 into 10 raised to power 14 to 4 into 10 raised to power 14, and the source is sun or any incandescent solid. Next is infrared rays, 7600 to 3 into 10 raised to power 7 wavelength, and the frequency is 4 into 10 raised to power 14 to 1 into 10 raised to power 11. The source is by vibration of molecules, example by heating rods of special materials. Next is microwaves with wavelength 3 into 10 raised to power 8 to 3 into 10 raised to power 11. The frequency is 1 into 10 raised to power 10 to 1 into 10 raised to power 7. And radio waves or TV waves have a wavelength 3 into 10 raised to power 7 to 3 into 10 raised to power 14 with frequency 1 into 10 raised to power 11 to 1 into 10 raised to power 4. Both microwaves and radio waves have the source by the oscillation of electrons in a wire, that is, from alternating electric current. Basic features of spectroscopy. Heading 3.3, Introduction to molecular spectroscopy and its difference from atomic spectroscopy. In case of atoms, when the energy is absorbed, the electrons jump to some outer orbit and then they start jumping back with the emission of energy equal to the difference between the energy of the two energy levels and the result in an atomic spectrum. However, in case of molecules, when the energy is absorbed, it may result into rotation, vibration or electronic transition depending upon the amount of energy absorbed. Just as electronic energy is quantized, that is, there are only discrete electronic energy levels in an atom or a molecule, the rotational and vibrational energy are also quantized, that is, they are only discrete rotational and vibrational energy levels in a molecule. The rotational, vibrational, and electronic energy levels of a molecule are collectively called molecular energy levels. The transitions of energies can take place only between these levels. The result is a molecular spectrum. When the energy absorbed by a molecule is so large that an electron can jump from the electronic energy level to another, then as the energy required for transition from one vibrational energy level to another is much less and from one rotational level to another is still less, hence the electronic transition is also accompanied by the transition between the vibrational levels as well as the rotational levels. The complete picture of the various molecular energy levels for the first two electronic levels is shown in figure 3.2. Thus, each electronic level consists of a number of vibrational sublevels represented by nu equals to 0, 1, 2, 3, etc. And further, each vibrational level consists of a number of rotational sublevels represented by j is equals to 0, 1, 2, 3, etc. V and J are called vibrational and rotational quantum numbers respectively. Because of a large number of energy levels involved for transition, it is evident that molecular spectra are much more complex than atomic spectra. However, just as atomic spectra help in the study of the structure of atoms, the study of molecular spectra gives even more information about the structure and properties of molecules such as bond lengths, bond angles, bond strengths, shapes, dipole moments, etc. Heading 3.4 Absorption and Emission Spectroscopy. As explained above, an atom or a molecule has a number of energy levels which are quantized. The transition takes place only between these energy levels according to certain rules called selection rules, as will be discussed later. The expression for the different types of energy levels of a molecule will be derived later in this chapter. However, at the moment, it is sufficient to know that the transition between any two energy levels can take place in either of the following two ways. First, the transition may take place from lower energy level to higher energy level by absorption energy. It is then called absorption spectroscopy, and the result obtained as a result of a number of such transition is called absorption spectrum. Second, the transition may take place from higher energy level to a lower energy level, thereby emitting the excess energy as a photon. It is then called emission spectroscopy, and the result obtained as a result of number of such transition is called emission spectrum. In fact, a number of groups of closely spaced lines are observed. Each such group of closely spaced line is called a band. Thus, a number of bands are observed. We can therefore conclude that whereas atoms give line spectra, molecules gives band spectra. In either case, the energy of the photon h nu emitted or absorbed is given by Bohr's frequency formula. E2 minus E1 is equals to h nu, or in terms of wavelength, lambda is equals to c upon nu, which is equals to hc upon E2 minus E1, or in terms of wave number, nu bar is equals to 1 upon lambda, which is equals to nu upon c in per centimeter if lambda is in centimeter or velocity c is in centimeter per second. It may be noted that emission and absorption spectroscopy give the same information about the energy levels separations. However, the practical considerations decide as to which technique should be used. Generally, absorption spectroscopy is used as absorption spectra are easier to interpret than emission spectra. Emission spectroscopy is used only when the visible or ultraviolet incident radiations are used. In this chapter, we shall therefore mainly concentrate on absorption spectroscopy. Heading 3.5 Experimental Setup. The instrument used for observing absorption spectrum of a substance is called absorption spectrometer, and its principle is shown in figure 3.4. It consists of mainly four parts, namely source of radiation, a slit to get a fine beam, a monochromator, that is a device for getting monochromatic, that is single frequency radiation. a sample cell, dispersing element which is either a glass or quartz prism or a diffraction grating, and detector. The nature of the components to be used depends upon the nature of the radiation, that is reason of the electromagnetic spectrum to be used, as shown as given in table 3.1. Next heading 3.6, signal to noise ratio. The analysis of any sample using an electronic instrument such as IR, UV or visible spectrometer consists of the following steps. First, the sample is allowed to interact with some kind of electromagnetic radiation. Some suitable energy is absorbed by the sample depending upon the nature of the sample. This is converted into an electric current detected by an electronic device called input transducer. The output of this transducer is known as signal. The second point is the electrical current is amplified and converted into voltage, etc. by a device known as electrical signal modifiers. Third, the modified electrical signals are then converted into information that can be read on a meter or recorded on a recorder. The device to do so is known as output transducer. Transducer is a device which receives waves from one source and supplies related waves not accessorily of the same type as the input to some other source. The signal produced may be considered to made up of two parts. First, due to the sample. Second, due to other components present along with the sample or the instrument used in the measurement. The signal produced due to part second is known as noise. In other words, noise represents unwanted, meaningless signals. Alternatively, noise may be defined as the random electronic signals that are usually visible as fluctuations of the baseline in the signal as shown in figure 3.5 below. Thus, the main aim of any precious measurement is to have noise reduction or signal enhancement. As the amount of radiation absorbed by the sample depends upon the concentration of the sample, the amount of noise present in an instrument determines the smallest concentration of the sample that can be accurately measured. As the concentration decreases to trace levels or the signal source are weak, as in case of C13 NMR spectroscopy, the problem of distinguishing signals from noise becomes more and more difficult, resulting in the decreased accuracy and precision in measurements. The ability of an instrument to distinguish between signals and noise is usually expressed in terms of signal to noise ratio S upon N, which in case of DC signals is given by S upon N is equals to average signal amplitude upon average noise amplitude. A higher value of S upon N implies greater noise reduction and hence a more precise measurement. It may be noted that the ratio S upon N cannot be increased by simply amplification because increase in the magnitude of signal is accompanied by a corresponding increase in the magnitude of the noise. The S upon N ratio can be enhanced by the following two ways. First, by hardware techniques, that is by using hardware devices such as filters, lock-in amplifiers, etc. Second, by software techniques, that is by using software algorithms such as ensemble averaging, boxcar averaging, Fourier transformation, etc. Software techniques have gained importance because of the built-in microcomputers in the modern instruments. Operations such as filtering, linearization and attenuation, etc., which were earlier accompanied by hardware devices, are now achieved by the software built-in microcomputer component of the instrument. The most powerful software technique for the enhancement of S upon N involves the mathematical operation known as Fourier transformations, FT. This is briefly described below. The conventional method of representing the data spectra by the detector is in the form of intensity of the radiation as function of frequency I. However, another method of representing the data spectrum through less common is in form of intensity of the radiation as a function of time f. Thus, there can be two types of spectra, one in the frequency domain and the other in the time domain. Contains all information about the spectrum that I contains and vice versa. I can be transformed into f through the following mathematical operation called Fourier transformations. F is equals to integration from minus infinity to plus infinity e raised to power 2 pi I v t I dv. Conversely, f can be transformed back into I by inverse Fourier transformation. I is equals to integration minus infinity to plus infinity e raised to power minus 2 pi I vt f dt. With a very small computer, it is possible to carry out the Fourier transformation of a spectrum in a few seconds. Though spectra are generally presented in the form of intensity as a function of frequency, that is, in the frequency domain I, yet it is found that it is useful to take the spectrum in the time domain f and then transform it into the usual I. The advantage of doing so is briefly explained below. To observe the spectrum in the frequency domain, a good deal of time is required because scanning has to be done gradually over a long range of frequencies. However, to observe the spectrum in the time domain, all frequency can be applied at once to the sample within a very short interval of time. Thus, it can be done only in a few seconds, unlike the frequency domain spectrum, which may require, say, 15 minutes to scan the spectrum. The spectroscopy based on Fourier transformation is known as Fourier transformation spectroscopy. For example, FT-NMR is very common nowadays. Similarly, we have FT-IR, FT-UV, etc. instead of conventional IR, UV, etc. In the FT spectroscopy, the data are rapidly generated in the time domain F, formed either by using an interferometer in case of optical spectroscopy or a pulsed nuclear magnetic resonance signal from a source of radio frequency. The resulting data are in the form of superimposed waves include all the frequency of the spectral range of the instrument. The resultant F is then transformed into I as shown in figure 3.6 on the previous page. The enhancement of S upon N ratio is achieved by using the time saved by rapid scanning. For example, in C13 NMR spectroscopy, approximately 1000 scans are required to extract the weak C13 signal from the noise. The FT technique requires 15 minutes to complete the scans, whereas the usual continuous wave CW method would require about 25 hours to obtain the same information. Heading 3.7 Resolving Power. The resolving power of a spectrometer is its ability to distinguish adjacent absorption bands or to vary close spectral lines as separate entities. Although prisms as dispersing elements have largely been superseded by diffraction gratings and interferometer, they are still used in spectroscopy. Further, taking prism as the dispersing medium, it is easy to understand the concept of dispersion and resolution as briefly explained below. Consider a prism whose base length is b. Suppose white light from a suitable source is allowed to fall on the face of the prism. After made parallel by lens L1, the prism disperses and dissolves the radiation which is focused by the lens L2 onto the detector as shown in figure 3.7 below. Suppose after dispersion, the two radiations separated out have wavelength lambda and lambda plus d lambda, or frequency nu and nu plus d nu, or wave number nu bar and nu bar plus d nu bar. Then the interval d lambda or dv or d nu bar is called resolution. If these intervals are small, we say that the prism has high resolution, and if these intervals are large, we say that the prism has low resolution. In general, the resolving power R of a dispersing element is defined by the expression R is equals to lambda upon d lambda is equals to nu upon d nu is equals to nu bar upon d nu bar. For a prism of base length b, if n is the refractive index of the material of the prism and the incident beam is sufficiently wide so that the extreme rays 1 and 2 fall on the edges of the face of the prism, the resolving power of the prism is given by R is equals to b dn upon d lambda. An interferometer is a device for analyzing the frequencies present in a composite signal. dn upon d lambda represents change in the refractive index of the material of the prism, which change in wavelength of the incident radiation. For high resolving power, dn upon d lambda should be large. In figure 3.7, if points P and P dash are separated by a distance dl, linear dispersion is defined as dl upon d lambda if the difference between the angles at which the rays going to P and P dash emerge from L2 is d theta, dl upon then angular dispersion is defined as d theta upon d lambda. Resolution gains significance in the study of absorption spectra because no molecular absorption takes place at a single frequency, but it always takes place over a spread range of frequencies, usually very narrow but sometimes quite large. Now the question arises, what are the factors on which the resolution d lambda depends? In addition to the nature of the dispersion material and the sensitivity of the detector, an important factor on which resolution depends is the width of the slit used before lens L1. Let us consider two lines close together as shown in figure 3.8, in which the dotted curves represent the absorption due to each line separately and solid line curve represents their combined absorption. If the exit slit width is larger than the separation between the lines, the twin absorption peaks pass steadily across the exit slit and then onto the detector to register the absorbance. In the final result, only one absorption peak is observed. Thus, the separation between the lines has disappeared under these conditions, that is, the lines are not resolved. Thus, it is evident that use of narrow slit would result in the resolution, that is, the resolving power would increase. In fact, if the slit width is less than the separation between the lines, the detector output will show a minimum between them. However, a narrower slit allows less total energy from the beam to reach the detector and consequently the signal strength will be less. There comes a point when further decreasing the slit width results in such weak signals that they become indistinguishable from the background noise. Thus, to get the best resolution, a proper choice of the minimum slit width is required consistent with the acceptable signal to noise ratio. Note that the dispersion power of a prism is not constant for a prism material, but it increases with longer wavelength to shorter wavelengths. This requires a knowledge of the refractive index of the dispersing material and its rate of change as a function of wavelength. A graph containing this information is provided by the supplier along with the instrument. It is just like the fact that if the entrance door and the exit door of a hole are quite wide, two persons may pass through together holding hand in hand and would look like a single entry or exit, whereas if the doors are narrow, only one person at a time can pass through, registering two separate entries or exit. Further, it is interesting to point out that when a narrow entrance slit is used, the detector registers not only one main peak but gives a diffraction pattern with a number of small peaks at plus or minus lambda, plus or minus 2 lambda, etc. from the central maximum as shown in figure 3.9. Thus, the wavelength lambda and lambda plus d lambda corresponding to points P and P dash, the two diffraction patterns are shown in figure 3.10. According to Rayleigh's criteria, the two wavelengths lambda and lambda plus d lambda are said to be resolved if central maximum of P dash is not closer to that of P than the first minimum of P. In case of diffraction grating, it consists of a series of parallel grooves on a hard glassy or metallic material. The grooves are extremely closely spaced, the spacing being usually of the order of 1 μm. For a grating, the resolving power is given by R is equals to Mn, where capital N is the total number of grooves and small m is the order of diffraction. For example, a grating ruled with 600 grooves per mm and 50 mm is in width has a resolving power of the first order is equals to 600 into 50, which is equals to 30,000. Thus, for sodium wavelength of 5,890 Armstrong, the smallest wavelength interval resolved will be del lambda is equals to 5,890 upon 30,000, which is equals to 0.2 Armstrong. Heading 3.8, Types of Molecular Energies and Bond of Mere Approximation. A molecule usually possesses 4 different types of energies. These are: first, translational energy, which is due to the translational motion of the molecules, that is, motion of the center of gravity. Second, rotational energy, which is due to the rotation of the molecule about an axis perpendicular to the internuclear axis. Third, vibrational energy, which is due to the to and fro motion of the nuclei to the molecule without any change in the position of the center of gravity of the molecule. Fourth, electronic energy, which is due to the absorption of energy by the electrons resulting in the transition from the lower electronic energy level to the higher energy level. According to Born-Oppenheimer approximation, the total energy of a molecule is the sum of translational, rotational, vibrational, and electronic energies. That is, E is equals to ET plus ER plus EV plus EE. Further, from the expression for the above different types of molecular energies, as will be derived later in this chapter and have been used earlier also in the previous chapter, it is found that the translational energy is negligible small. Hence, Born-Oppenheimer approximation can be written as E is equals to ER plus EV plus EE. Heading 3.9, Types of Molecular Spectra. As explained earlier, a molecule has different types of quantized energy levels, that is translational, rotational, vibrational, and electronic. The molecular spectra arise due to transition taking place between these energy levels. The energy absorbed for any transition is equal to the difference in the energy of the two levels involved. It is found that these energies for transition are in the order ET lesser than ER, which is lesser than EV, and the largest is EE. In fact, the difference between the successive translational energy levels is so small that it cannot be observed experimentally. For this reason, for practical purpose, translational energies is considered as continuous and we do not observe any translational spectrum. The different types of molecular spectra are generally observed depending upon the energy absorbed, and the reasons of the electronic magnetic spectra in which they are observed are shown in figure 3.11 and are briefly explained below. First, pure rotational microwave spectra. If the energy absorbed by the molecule is so low that it can cause transition only from one rotational level to another within the same vibrational level, the result obtained is called the rotational spectrum. These spectra are therefore observed in the far infrared region or in the microwave region, whose energies are exceedingly small. The spectra obtained is therefore also called microwave spectra. Second, vibrational rotational spectra. If the exciting energy is sufficiently large so that it can cause a transition from one vibration level to another within the same electronic level, then as the energies required for the transition between the rotational level are still less, both types of transition will take place in the result is therefore a vibration rotational spectrum. Since such energies are available in the near infrared region, these spectra are observed in this region and are also called infrared spectra. Third, electronic band spectra. If the exciting energy is still higher such that it can result in a transition from one electronic level to another, then this will also be accompanied by vibrational level changes, and each of these is further accompanied by rotational level changes. For each vibrational change, a set of closely spaced lines is observed due to rotational level change. Such a group of closely spaced rotational lines is called a band. Thus, for a given electronic transition, a set of bands is observed. This set of bands is called band group or a band system. Each electronic transition gives a band system. The complete set of band system obtained due to different electronic transitions gives the electronic band spectrum of the gaseous molecule. Thus, whereas atoms give line spectra, molecules give band spectra. As such high excitation energies are available in the visible and ultraviolet regions, these spectra are observed in the visible regions and ultraviolet region. Strictly speaking, we would write EE minus EE is the largest, then EV dash minus EV dash dash, and then lesser is ER minus ER double dash, and the lowest is ET dash minus ET dash dash, where single prime refers to the state of higher energy and double prime to the state of lower energy. Fourth, Raman spectra. This is also type of vibrational rotational spectrum but is based on scattering of radiation and not on the absorption of radiation by the sample. It is based upon the principle that when a sample is hit by monochromatic radiation of the visible region and scattering is observed at right angle to the direction of the incident beam, the scattered radiation have frequency equal to the incident beam as well as frequency different than that of the incident beam. The difference in the frequency of the incident beam and that of scattered beam are similar to those needed for the vibrational and rotational transitions. However, by suitably adjusting the frequency of the incident radiation, Raman spectra are observed in the visible region. Fifth, nuclear magnetic resonance NMR spectra. This type of spectrum arises from the transition between the nuclear spin energy levels of the molecule. When an external magnetic field is applied on it, the energies involved in this transition are very high, which lie in the ratio frequency region. The method is based upon applying such frequency on the sample so that it is in the resonance with the applied frequency. Sixth, electron spin resonance ESR spectra. This type of spectrum arises from the transition between the electron spin energy level of the molecule when an external magnetic field is applied on it. These involve frequency corresponding to microwave region. Frequencies of this region are applied on the sample to bring the sample in resonance condition. Heading 3.10 Selection Rules. We know that atomic spectra as well as molecular spectra are obtained due to transition taking place between different energy levels. However, such transition can take place only between definite energy levels and not between any two energy levels. The restrictions thus applied on the transitions are governed by certain rules which are called the selection rules. If these rules are followed, the transition can take place and it is called as allowed transition. If these rules are not followed, the transition cannot take place and it is called as forbidden transition. The selection rules to be followed depend upon the type of transition. However, the fundamental principle on the basis of which the selection rules are derived is that for a molecule to interact with the electromagnetic radiation and to absorb or emit a photon of frequency nu, it must possess a dipole at the frequency, the dipole moment of which is called the transition dipole moment. The intensity of the transition is proportional to the square of the transition dipole moment. Thus, a transition is allowed only if nu Tr is not equals to 0. For example, rotational transition moment is 0 unless the molecule has a permanent dipole moment. Hence, pure rotational spectra are observed only for molecules which have permanent dipole moment. That example NO, CO, etc. A gross selection rule specifies the general features that a molecule must have in order to give a particular type of spectrum. The specific selection rules are generally expressed in terms of changes in quantum numbers for the allowed transition. For example, for the pure rotational transition, the selection rule is del J is equals to plus minus 1, where J represents rotational quantum number. Similarly, for pure vibrational transition, the selection rule is del nu is equals to plus minus 1, where nu represents the vibrational quantum number. Further details of these rules will be discussed at the relevant sections. Heading 3.11 Widths and intensities of the spectral lines. In any type of molecular spectroscopy, the two important characteristics of any spectral lines are: first, how sharp is the line. This is decided by the width of line. Second, how strong is the line. This is decided by the intensity of the line. A width of the spectral line is sharp. It will have no width as shown in figure 3.13. On the other hand, if the line is not sharp, it will have a certain width as shown in figure 3.12. That is, it spreads over a range of frequencies. In case of atomic spectra, the selection rules are derived by identifying the transitions in which angular momentum is conserved when a photon is emitted or absorbed. For example, for the hydrogenic atoms, the selection rules are del I is equals to plus minus 1, del ml is equals to 0 or plus minus 1. The principal quantum number can change by any amount because it is not directly related to the angular momentum. For example, for 4D orbital, L is equals to 2. Therefore, electron from a 4D orbital can make a transition to any NS or ND orbital is forbidden. Factors affecting the width of spectral lines. The two factors which contribute to the broadening of a spectral line are: first, Doppler broadening, and second, lifetime broadening. These are briefly discussed below. First, Doppler broadening. This type of broadening occurs due to Doppler effect, according to which in a gaseous sample, frequency of the radiation emitted or absorbed change when the molecule is moving towards or away from the observer or the observing instrument. Doppler effect is applicable to gaseous samples because, according to kinetic theory of gases, the molecules of a gas are continuously moving in a zigzag manner. If the molecule emitting the frequency nu is moving away from the observer with a velocity nu, the observer detects radiation of frequency V dash is equals to V upon 1 plus nu upon C. where c is the velocity of light. If the molecules is approaching the observer, then it appears to emit radiation of frequency v dash is equals to v upon 1 minus nu upon c. The difference v minus v dash is equals to del v is called Doppler broadening or Doppler shift. Since in a gas the molecules are moving in different direction with the different speeds, some of them are moving away from the observer, therefore the detected spectral line arises from all the resulting Doppler shift. As the speeds of a gas molecule at a particular temperature are given by Maxwell distribution, therefore the shape of Doppler line is similar to that of Maxwell distribution of speeds as shown in figure 3.12 or figure 3.13. Further, it is found by calculations that if m is the mass of the gas molecule, then the temperature T, the width of line at half the height is del V is equals to 2V upon C into 2 kT ln 2 upon m raised to power half. Lastly, it may be pointed out that Doppler broadening increases the increase in temperature because the molecular speeds increase with increase in temperature. Hence, to obtain spectra of maximum sharpness, it is best to work at a low temperature. Second, lifetime broadening. This type of broadening occurs in all types of samples, that is gaseous, liquid, solids or solution. It arises because when Schrödinger equation is solved for a system that is changing with time, it is impossible to specify the energy of the levels exactly. If on the average a system survives in a state for time t, then the energy levels are blurred to an extent of del E, where del E is equals to h upon 2 pi t, which is equals to h upon t. The quantity del E is called lifetime broadening. Equation 4 reminds us to the Hinsberg's uncertainty principle, and hence the quantity del E or del nu bar in the above equation is called uncertainty broadening. From equation 4, we observe that del E is proportional to 1 upon T, thus shorter the lifetime of the state involved in the transition, greater is the broadening of the spectral line. As no excited state has an indefinite lifetime, therefore all states are subject to some lifetime broadening. The main reason for the finite lifetimes of the excited state is the collisions between the molecules or with the walls of the container. If the mean time between collisions is T collision, then the width of the resulting line del E collision is equals to h upon 2 pi T collision, which is equals to h upon T collision. In a gaseous sample, the collisional lifetime can be increased and hence broadening minimized by working at low pressures. The transition from an excited state to a lower state is a natural phenomena, the rate of which cannot be changed by changing the conditions. Thus, depending upon the natural limit to the lifetime of the excited state, the broadening that results is called natural line width of the transition. However, the natural line widths are so small that the collisions and Doppler line broadening dominate. B. Intensity of the spectral line. The strength or intensity of a spectral line depends upon first, population of states with the particular energy in the initial state. Second, the strength of the incident radiation. Third, the probability that a transition will take place between the energy levels. The probability of transition is decided by the selection rules. If the transition is allowed, a strong spectral line will be obtained. If it is forbidden, no spectral line will be obtained. Similarly, greater is the intensity of the incident radiation, greater is the ratio at which the transition are induced, and hence stronger is the absorption of the sample. To explain how the population density of the states involved in the transition affect the intensity of the spectral lines, Einstein suggested that the net rate of absorption in the presence of an electromagnetic field is the resultant of the following three processes. First, stimulated absorption. Second, stimulated emission. Third, spontaneous emission. These are shown diagrammatically in figure 3.14. Stimulated absorption is the transition from a lower energy state to a higher energy state by absorbing suitable frequency from the incident radiation, that is, the process has been stimulated by the incident radiation. According to Einstein, the rate at which it occurs is given by R is equals to Bp, where the constant B is called Einstein coefficient of stimulated absorption and P is the energy density of the radiation at the frequency of the transition. Equation 6 represents the rate of absorption for single molecule. For n molecules present in the lower state, the total rate of absorption for transition will be R is equals to n into small r is equals to nbp. Einstein suggested that the radiation was able to induce a molecule in the upper state to undergo a transition to the lower state and hence produce a photon of frequency v. This is called stimulated emission. The rate of stimulated emission is given by R dash is equals to B dash P, where B dash is called Einstein coefficient of stimulated emission. Note that only radiation of the same frequency as required for transition can stimulate an excited state to fall to a lower state. Einstein further suggested that the excited state could return to the lower state not only by stimulated emission but also by spontaneous emission at a rate independent of the intensity of incident radiation. Hence, the total rate of transition to a lower state is given by R dash is equals to A plus B dash P, where the constant A is called Einstein coefficient of spontaneous emission. Thus, for n dash molecules in the upper state, the total rate of emission will be R dash is equals to n dash into A plus B dash P, where n dash is the population of the upper state. At relatively low frequencies, the spontaneous emission can be ignored. Hence, we can write R dash is equals to n dash B dash P. From equation 7 and 11, the net ratio of absorption is given by R net is equals to NBP minus N dash B dash P, which is equals to N minus N dash into BP. Thus, the net absorption is proportional to the population difference of the two states involved in the transition. Hence, the intensities will be proportional to the population difference between the two states. At any temperature T, the ratio of the populations of the two states with energy E and E dash can be obtained by applying Boltzmann distribution law. N dash upon N is equals to E raised to power minus HV upon KT, where HV is equals to E dash minus E is equals to del E. If del E is large, the ratio N dash by N will be small. This will imply that the population in the upper state is small. Hence, the only significant absorption will be from the lower state and the stimulated emission from the upper state will also be negligible. Heading 3.12 Degrees of freedom of motion. Consider a molecule made up of n atoms. Since almost all the mass of the atom is concentrated in its nucleus and the nucleus is very small in size, the atoms may be considered as mass points. To represent each mass point, we require 3 coordinates. Hence, to represent the instantaneous position of n mass points in space, we require 3n coordinates. The number of the coordinates required to specify the position of all the mass points, that is atoms in a molecule, is called the number of degrees of freedom. Thus, a molecule made up of n atoms has 3n degrees of freedom. According to kinetic theory of matter, when thermal energy is absorbed by a molecule, it is stored within the molecule in form of first translational motion of the molecule, second internal movement of the atoms within the molecules, that is rotational motion and vibrational motion. The translation motion of the molecule means the motion of center of mass of the molecule as a whole. The center of mass of the molecule can be represented by 3 coordinates. Hence, there are 3 translational degrees of freedom. The remaining coordinates represent the internal degrees of freedom. However, as already mentioned, the internal degrees of freedom may be subdivided into first rotational degrees of freedom and second vibrational degrees of freedom. For a rotational motion, there are 2 degrees of freedom for a linear molecule and 3 for a non-linear molecule. Remaining degrees of freedom for the linear molecule are equal to 3n minus 5, and for the non-linear molecules they are equal to 3n minus 6. These describe the motion of the nuclei with respect to one another and thus represent the number of vibrational degrees of freedom. Hence, vibrational degrees of freedom of a linear molecule containing n atoms is equals to 3n minus 5. Vibrational degrees of freedom of non-linear molecule containing n atoms is equals to 3n minus 6. A few examples on the calculation of vibrational degrees of freedom are given below. First, as a diatomic molecule is always linear, its vibrational degrees of freedom is equals to 3n minus 5, that is 3 into 2 minus 5, which is 1. Second, for the linear polyatomic molecule CO2, n is equals to 3. Hence, vibrational degrees of freedom 3n minus 5 is equals to 3 into 3 minus 5, which is 4. Similarly, for HC, triple bond with CH, n is equals to 4, hence the vibrational degrees of freedom is equals to 3n minus 5, 3, which is 3 into 4 minus 5 is equals to 7. Third, for the non-linear polyatomic molecule H2O, n is equals to 3. Hence, vibrational degrees of freedom is equals to 3n minus 6 is equals to 3 into 3 minus 6, which is 3. Similarly, for HCHO, n is equals to 4. The vibrational degrees of freedom is equals to 3n minus 6 is equals to 3 into 4 minus 6, which is 6. In terms of coordinates, the vibrational degree of freedom represents the interatomic distance and the angle needed to specify the geometry of the atomic framework within the molecule. In terms of molecular motion, the vibrational degrees of freedom represent the number of independent vibrational modes that can occur in the molecule, the vibrational energy being associated with each mode. The only one mode of vibration of a diatomic molecule like CO, 4 modes of vibration of linear triatomic CO2 molecule, and 3 modes of vibration of non-linear triatomic H2O molecule are shown in figure 3.16. To sum up, for a molecule made up of n atoms, total degree of freedom is equals to 3n. Further split up of these is as follows. For linear molecule, translational is 3, rotational is 2, and vibrational is 3n minus 5. For a non-linear molecule, translational is 3, rotational is 3, and vibrational is 3n minus 6. Now we shall take up the study of the different types of spectra one by one. Pure rotational spectra of diatomic molecules. Heading 3.13. Energy levels of a rigid rotor. On the basis of wave mechanics, it can be seen that if diatomic molecule is considered to be a rigid rotator, that is like a rigid dumbbell joined along its line of centers by a bond equal to length to the distance r0 between the two nuclei, then allowed rotational energy of the molecule around the axis passing through the center of gravity and perpendicular to the line joining the nuclei are given by Er is equals to h square upon 8 pi square I into j plus 1, where j is the rotational quantum number that can have values 0, 1, 2, 3, etc. and I is the moment of inertia of the molecule about the axis of rotation, that is I is equals to m1 into m2 upon m1 plus m2 into r0 square, which is equals to mu r0 square, where m1 and m2 are the atomic masses of the two atoms of the diatomic molecule, and m1 m2 upon m1 plus m2 is equals to nu is called reduced mass. Derivation of the expression for rotational energy. Center of gravity of a diatomic molecule is the point which satisfies the following condition. M1 R1 is equals to M2 R2. The moment of inertia of the diatomic molecule is given by I is equals to M1 R1 square plus M2 R2 square, which is equals to M2 R2 R1 plus M1 R1 R2 is equals to R1 R2 into M1 plus M2. But R1 plus R2 is equals to R0. Therefore, from equation 4, M1 R1 is equals to M2 into R0 minus R1, or R1 is equals to M2 R0 upon M1 plus M2. Similarly, R2 is equals to M1 R0 upon M1 plus M2. Substituting these values in equation 5, we get I is equals to M1 M2 square upon M1 plus M2 whole square into R0 square plus M1 square M2 upon M1 plus M2 whole square into R0 square, which is equals to m1 m2 into m1 plus m2 upon m1 plus m2 whole square into r0 square, which is equals to m1 m2 upon m1 plus m2 into r0 square is equals to mu r0 square. Now, by definition, the angular momentum of rotating a molecule is given by L is equals to I omega, where omega is the angular velocity. But we know that angular momentum is quantized, whose values are given by L is equals to root over j into j plus 1 into h upon 2 pi, where j is equals to 0, 1, 2, 3, etc. called the rotational quantum numbers. Further, the energy of a rotating molecule is given by E is equals to I omega square. Therefore, the quantized value of the rotational energy will be given by ER is equals to half I omega square is equals to L square upon 2I. Substituting the values of L from equation 12, we get ER is equals to j into j plus 1 into h square upon 4 pi square into 1 upon 2I. Or ER is equals to h square upon 8 pi square I into j plus 1. Putting j is equals to 0, 1, 2, 3, etc. In equation 1, pattern of rotational energy level obtained will be as shown in figure 3.18. Evidently, the spacing between the energy levels increasing as j increases. Heading 3.14 Rotational Selection Rules. According to the selection rules, the transition take place only between those rotational energy level for which del j is equals to plus minus 1. That is, the change in the rotational quantum number is unity. The transition del j is equals to plus 1 corresponds to absorption and j is equals to minus 1 corresponds to emission. In other words, a transition can take place from a particular rotational level to just the next higher or just the lower rotational level. All these transitions can take place with equal probability, whereas all other transitions are forbidden. Heading 3.15 Rotational Spectra of the Diatomic Molecules. As already explained, the allowed rotational energies are given by the expression ER is equals to h square upon 8 pi square I into j plus 1. As E is equals to h nu, therefore in terms of frequency we can write nu is equals to h upon 8 pi square I into j plus 1. Further, as C is equals to nu lambda is equals to V by V bar, because wave number V bar is equals to 1 upon lambda. Therefore, in terms of wave number, equation 2 can be written as nu bar is equals to h upon 8 pi square IC into j plus 1, which is equals to bj into j plus 1. Putting b is equals to h upon 8 pi square IC is called rotational constant. Putting j is equals to 0, 1, 2, 3, etc. in equation 4, the wave number of the different rotational levels will be 0, 2b, 6b, 12b, 20b, 30b, and so on. When a transition takes place from a lower rotational level with rotational quantum number j to a higher rotational level with rotational quantum number j dash, the energy absorbed will be given by del ER is equals to ER dash minus ER, which is equals to h square 8 pi square I into j dash plus 1 minus j into j plus 1. However, according to the rotational selection rules, only those rotational transitions are allowed for which del j is equals to plus minus 1. Hence, in the present case, j dash is equals to j plus 1. Substituting these values in equation 5, we get del ER is equals to h square upon 8 pi square I into 2 into j plus 1. To express in terms of wave numbers, we put del ER is equals to h nu, which is equals to h upon c lambda, which is equals to hc into nu bar. Hence, hc nu bar is equals to h square upon 8 pi square I into 2 into j plus 1. Or nu bar is equals to h upon 8 pi square IC into 2 into j plus 1, which is equals to 2b j plus 1, where b is equals to h upon 8 pi square IC is rotational constant as already explained. Strictly speaking, here we should write del nu and del nu bar in place of nu and nu bar. Nu bar in equation 7 represent the wave number of the spectral lines which will be obtained as a result of the transition between the rotational level. Putting j is equals to 0, 1, 2, 3, etc. or in general form j to j plus 1 involving absorption of energy, the wave number of the lines obtained will be 2b, 4b, 6b, 8b, and so on. We find that the most important feature of the pure rotational spectrum is that every two successive lines have a constant difference of a wave number equal to 2b. This is called frequency separation. Thus, the various lines of the rotational spectra will be equally spaced. Thus, the separation between any two successive lines will have the difference in wave number given by del nu bar is equals to 2b is equals to h upon 4 pi square IC. Another important feature of the spectra is that the intensities of the different transition are not equal. The intensities increase with increasing j, pass through a maximum and then decrease as j further increases. The explanation of this observation is discussed in the next section. However, the main feature of a rotational spectrum may be shown in figure 3.19. Heading 3.16 Relative intensities or rotational spectral lines. It is expected that the relative intensities of the spectral lines will depend upon the relative population of the energy level. Greater is the population of an energy level, greater is the number of molecules that can be promoted to the next higher level, and hence greater is the intensity of absorption. But the population of a rotational energy level with the quantum number J is given according to Boltzmann distribution law by the equation Nj upon N naught is equals to e raised to power minus Ej upon kt. However, rotational energy level are degenerate, and the degeneracy of any rotational level with the quantum number j is given by Gj is equals to 2j plus 1. Thus, the relative population of an energy level and hence intensity of the rotation line will be proportional to the product of both the above factors. That is, intensity is proportional to Nj upon N naught is equals to 2j plus 1 into e raised to power minus capital Ej upon kt. Putting Ej is equals to h nu is equals to hc by lambda is equals to hc nu bar is equals to hc bj into j plus 1. We get Nj upon N naught is equals to 2j plus 1 e raised to power minus hc bj into j plus 1 whole upon kt. As j increases, the first factor 2j plus 1 increases, whereas the exponential factor decreases slowly in the beginning and then rapidly as the value of j become higher and higher. Hence, plot of Nj upon N naught versus J for a rigid diatomic molecule is obtained as shown in figure 3.20. This graph clearly shows the relative population and hence the intensity of transition first increases, reaches a maximum value and then decreases. Heading 3.17. Types of molecules exhibiting rotational spectra. As already explained, the Gauss selection rule for the observation of a pure rotational spectrum is that the molecule must have a permanent dipole moment so that it can interact with the electromagnetic radiation and absorb or emit a photon. Thus, pure rotational spectrum is given only by polar molecules. Consequently, homonuclear diatomic molecules and symmetrical linear molecules like NO2 do not give rotational spectra. Thus, polar molecules like NO, N2O, etc. gives pure rotational spectra. Heading 3.18. Structural information from rotational spectra. Calculation of moment of inertia and bond length from rotational spectra. From the study of the rotational spectrum, that is by determining the frequency separation del nu bar, it is possible to calculate the moment of inertia I of the molecule using equation B is equals to h upon 8 pi square IC. Then, knowing the masses of the atoms present in diatomic molecule, it is possible to calculate the distance between the atoms R naught, that is internuclear distance or bond length, using equation 2, section 3.13. Next heading 3.19. Experimental details of microwave spectroscopy. The source of radiation is a special type of electronic oscillator called klystron. It produces monochromatic radiation of frequency corresponding to wavelength range of 0.1 to few hundred transitions. The procedure consists in passing the monochromatic energy of microwave through the gaseous sample of the substance being studied and measuring the intensity of the transmitted radiation. By varying the frequency of oscillator and observing the intensity of the transmitted beams, the frequency at which absorption takes place can be determined. From these data, the structural parameters like the moment of inertia, internuclear distance, etc. can be calculated. Then there are numerical problems on rotational spectra. Next heading 3.20. Non-rigid rotator, a qualitative description. As explained in equation second, section 3.15, the frequency of rotation of rigid rotator is given by nu is equals to h upon 8 pi square I into j plus 1. Thus, the frequency of rotation increase with increase in rotational quantum number j. But the increase in the frequency of rotation increases the centrifugal force which tends to move the atoms apart. This implies that the bond length of the diatomic molecule increases with increase in the value of J. Thus, the molecule will no longer behave as a rigid rotator. Instead, it will behave like a non-rigid rotator. Also, it was explained in equation 4, section 3.15 that the wave number of the rotational levels of a rigid rotor are given by nu bar is equals to bj into j plus 1. For a molecule behaving like non-rigid rotator, the wave number of the rotational level are given by nu bar is equals to bj into j plus 1 minus dj square into j plus 1 whole square, where d is called centrifugal distortion constant and is related to the force constant K of the bond. Thus, when a transition takes place from rotational level J to J plus 1, the wave number of the line produced if the molecule behaves like non-rigid rotor will be given by del nu bar is equals to nu bar J plus 1 minus nu bar J, which is equals to 2 into J plus 1 into B minus 2D into J plus 1 whole square. Now, as J increases, the factor B minus 2D into J plus 1 whole square decreases. Hence, del nu bar decreases with increase in the value of J. Next heading 3.21 Isotopic effect. If in a molecule an atom is replaced by its isotope, chemically the new molecule is no different from the original molecule with respect to electron distribution, internuclear distance or dipole moment. However, because of the difference in mass of the isotope, the moment of inertia of the molecule changes, as B is equals to h upon 8 pi square IC, that is I appears in the denominator. This means that if I increases, B will decrease. As the energy of the rotational level are directly related to the value of B, hence the energy of rotational level will decrease, that is the energy level will come closer. Otherwise too, as the spacing between the adjacent energy level is equals to 2b, decrease in the value of B means that the energy levels will come closer. From the study of rotational spectra with isotopic substitution, it is possible to calculate not only the atomic mass of the isotope but also their relative abundance by comparing the absorption. Thank you.